All right, friends and neighbors, we're going to get serious for this networking video. We're going to do some subnetting examples because, hey, they're challenging, and the more we do, the better off we're going to be. So let's dive in. Now, before we take a look at subnetting, or supernetting for that matter, now before we dive into mask manipulation, let's remember that we started with class-full addressing. And class-full addressing, for hosts anyway, we talk about class A, B, and C. And we know that in a Class A network, the first octet of the IP address is going to be in the range of 0 to 127. And then we're going to have a default mask of 255.0.0.0. And Class Bs begin with 128 to 191. They have their own default mask. Class Cs fall in the range of 192 to 223 and then have their own default mask of 255, 255, 255.0. Now, we don't use the class-full addressing today. Why? Because it's wasteful. It's terribly inefficient. So we manipulate the mask all the time. Now, I won't get into the other addresses that are part of these address space. We did videos on those. So, for example, 127 is used. We've got private addressing out there all over the place. Look at the other videos for that. We are going to do subnetting today. So let's also remind ourselves about why we do those two things and how the operations actually work. When we start fooling around with the mask, we're either going to be doing subnetting or supernetting. Now for subnetting, we are trying to reduce the size of the address space that we're working with. So if a class C has 256 possible addresses, we want to work with a smaller address space, and we do that by breaking up the class full address space into smaller chunks. All right. Why do we do that? Well, we want an appropriately sized network. We want problem containment. We want to handle security issues, quality of service mechanisms. We want to control broadcast traffic. There's just all kinds of reasons why we want smaller address spaces. The way that we get smaller address spaces is that we change the bits in the host portion of the mask. So when we're dealing with subnetting, we're looking at the zeros in the mask and we're going to convert those to ones. And when we're dealing with supernetting, also known as aggregation, then we are increasing the size of the address space, which is the exact opposite. The real main reason that we do that is because we want to reduce routing table sizes. How do we do that? Well, when we manipulate the mask and we aggregate things together, that means that we can collapse several routing table entries into one as long as it's continuous address space. So it makes routing more efficient. The way that we do that is we change bits in the network portion of the mask. So we're going to convert ones to zeros. On top of all this, we have to sort of remember that we're out of IPv4 address space. So you just can't say, hey, can I have a new Class B or Class C address space? All right, so let's do some examples. Now I'm going to do this manually for this video so that you can see exactly what I'm doing. Our first one that we're going to start off with is a Class C address. And I've just picked some random numbers, 210.205.200.0 as my Class C address. And that means that we have a default mask of 255, 255, 255.0. Now another way to write this is with the CIDR notation, the classless interdomain routing notation, and so in this case it would be a /24. And that means that I'm just counting the binary ones in the mask. Now the first question that we ask is, how many subnets do we want? And for this one, we'll start off with the example of 4. We'll make it really, really straightforward. Okay, we say 4. Now, there's two ways to do subnetting and supernetting problems, and I'm going to show you both as I always do, but remember that it's really all about the binary. When problems get difficult, you have to do the binary, otherwise it's really easy to make mistakes. But I'll show you both ways. Now, if we remember that the class full address space of a Class C is 256 possible addresses, and we just said that the number of subnets I want to create is 4, so we're going to now divide that by 4. And what does that give us? That gives us the number of hosts that are going to be part of the new subnet address space in each subnet. So this gives us 64. Okay, so the next thing that we need to ask is, how many bits do we need to convert in the host portion of the subnet mask or the net mask? So now we say, all right, how many bits are changed? I also like to call these stolen, so we're going to steal these from the host portion. And the answer to that is 2. We're going to steal 2 bits. Why do we steal 2 bits? Because there are 4 possibilities in 2 bits. So 0, 0, 0, 1, 1, 0, and 1, 1. Those are my 4 possibilities, and those are going to help me identify the host portion changes and the new subnet IDs. All right, so now the next question would be, maybe, what's the new mask? Well, if I steal 2 bits, and where we would do that is right here. So I'm actually going to separate this right here. So what I would do is I would change this, change those 2 bits right there to 1s. That's how I manipulate the mask. So now I'm dealing with a new mask, and so the new mask would be 255, 255, 255, 192. All right. Now this portion above us, in what we might call the match criteria, right there, that now becomes our subnet field, and that is where we're going to see our binary patterns. Now the next thing to remember is when we do subnetting, we are going to always, always, always start with the class full address space, but with the new mask. So down here I can say that my first subnet is 210.205, trying to do my spacing, .200.0. So I start right there. Now if we look at the binary for this octet, it turns out that right now it is all zeros. And I'm going to remember that those first 2 bits right there are my subnet field. Okay. Now, when we have a class full address space, the range of host addresses here is 0 to 255. We know that that's the range because if I put anything right here and I do my ANDing process when I'm figuring out the network, I'll be ANDing with zeros, binary zeros. So it doesn't matter what I put here, I will always get that the network is .0. Remember that the whole point of the network mask underneath an IP address is to tell you what network you're sitting on. When I put all zeros in the host portion, and this doesn't matter if we're talking about class full addressing or subnetting or supernetting. When I put all zeros in the host portion, what I get is the network ID, or in this case the subnet ID, which happens to be .0. When I put all ones in the host portion, that is to say the highest possible address in that range, then I'm getting the directed broadcast at that particular network. Well, what does that look like? Well, I'm just going to copy these over like this, and I'm now going to convert this to all ones. So, not manipulating the mask or the subnet here, just dealing with the ranges, the maximum number of addresses that when ANDed with the mask, I get the same value. And it turns out that this value is 63. So, again, if I say like that, that gives me my subnet range. And maybe what we'll do is we'll say this was .63, like that. What is the next subnet? Well, the next subnet is simply going to be one more than this highest value in the first subnet. And we'll line these up nice. So still 210, 205, 200. Whoops. We'll line up my columns here. Now, the next number here is 64. So I'm just going to put that here. But watch what happens when we do the binary for 64. It looks like this. Okay? This becomes the next pattern in my binary. So here's the subnet field that I've been dealing with. And look at that. 64 has the next possible value of that 2-bit pattern. So maybe I'll put those up here. 00, 01, 10, 11. Now, if I follow the same rule and I put all ones in the host portion, then what I'm doing is saying 64 plus 63, or just I would do the addition and I would get 127. So what does that look like? Like that. And again, same subnet field. Okay, so the range of possible values in my first subnet is 0 to 63. And my host portion has shrunk here, right? I have 6 bits of addressing for hosts instead of 8. Now another way to look at this is, how many hosts can I squeeze into 6 bits? And the answer is 64. But we start counting at 0, so we go 0 to 63. The next value is 64. 64 to 127 is 64 possible values. All right, what is the third subnet? And to make my life easier, we'll just copy this. Well, what's one more than 127? It's 128. Well, what does that look like in binary? It looks like this. Notice again that my subnetting field just changed to this next possible value. Well, 128 plus 63 gives us 191. There we go. The binary will never fail you. If you break this out like I've done here, and you take a look at the subnetting field, and you just simply put all zeros in the host portion and then all ones in the host portion, whatever the host portion is going to be, then you know that you've done this correctly. It doesn't matter what value I put here, as long as I remember that my subnetting field is 2 bits and I put in all zeros and all ones. All right. Well, our fourth subnet follows the same rule. The next number is 192. Oop. What does 192 look like? There we go. There's our next binary value. Well, the last octet in the range, so this is just another check, right? The last subnet will also have the highest possible address in the class full address space, which was 255. So we know that it's going to be 255, but a check for us is to say, well, my subnet field is 11. I'm going to put all ones in the host portion, right? And there we have 255. Okay, now to keep us going here, what would a router be in this particular subnetting scheme? Well, I like routers that are high in the range of addresses. So I always give my routers the highest possible host. But this brings up another question. I have done subnetting, and the whole point was to reduce the size of the address spaces that I was using. I created 4 of them, but all of them are smaller than the class full address space. Each one of them has a low and high address. Each one of them has that subnet ID, the lowest, and the broadcast ID, the highest. That means that of those 64 possible addresses, I used 2 already. One for the subnet ID and one for the broadcast. So how many usable addresses are there? Well, it turns out that there are 62 possible addresses now in each. Maybe I'll give you a column header for this. Usable addresses is 62 for each one of these. Because we had to burn 2 for the network ID and for the broadcast. All right, so what might be a possible router then in each one of these subnets? Well, if we pick the highest possible address and we applied that to the routers, then in this case I would say it would be 210.205.200.62. Let's be really clear about something else here too. The values that I'm talking about are 1 to 62 here. The values that I'm talking about here are what? Well, they'd be 65 to 126. And here, the values would be 129 to 190. And the values here would be 193 to 254. There's our old friend, the router that we like to use. All right, so here, my router might be 126. The router here, I guess we can tab over one more time. The router here might be 190. And here might be 254. So again, high in the range. The hosts would be the other usable addresses. All right, so there's a Class C example. Now, we always do Class C examples because they're easy to deal with. Let's try a Class B, and we'll do more subnets. Okay, so here we are with a Class B, completely different address space. I chose, a private address space, but it doesn't really matter whether it's public or private. We can still do subnetting. So it's all about the binary. So our question is, how many subnets do we want to create? Well, without getting too nutty here, right, let's just do, say, 8. So here I would do 8. And let's do our basic math. Well, a Class B address space is 65,536. Oh my goodness, I don't know if I can do this. Divided by 8. So what we're trying to figure out here is how many hosts are going to be in our particular subnet. Well, that's really hard. Well, we can sort of ballpark it, right? What's 64 divided by 8? It's 8. So this would be a power of 2. So if this is 65,000 addresses in here, in this address space, and we know that to create 8 possibilities, I'm going to steal 3 bits, then really what I'm dealing with is an address space that's, we'll do it like this, right? So this is the amount of bits that I have now for my host portion of the subnetting. So we could do this with the binary, right? How many bits or how many hosts per subnet? Well, we know that 1 byte is 256. We've got another bit here, 512, 1024, 2048, 4096, 8192. So this comes out to 8192. Okay. Well, let's highlight what we know to be our subnet field now and the bits that we're going to steal. Well, the way that we steal those, remember that we're going to convert those to ones. All right. Well, what was the range of possible addresses in this space to begin with? Well, it was, as it says over there in the class full address space, 192.168 or 172.16.00 to 172.16.255.255. This address is pretty straightforward. It's this one right here, all zeros in the host portion. Well, for the class full address space, we would put all ones in the host portion. And that, of course, looks like this. And that gives us this address right here. All right, so maybe we won't do all of these subnets in the interest of time, but let's do like the first three. Let's obey our rules. And we'll say, what's the first subnet? Oh, let's do this first. What would be the new mask if we stole 3 bits here? Well, 255, 255, what's this new mask? Well, it would be 255.255.224.0. The CIDR notation for this mask up here is /16. The CIDR notation for this mask is /19. So the first subnet, obeying the rules, we start with the class full address space, 172.16.00, which looks like this. Okay. And maybe what I'll do is, we'll take a couple of lines to do this maybe. So that's our first subnet. And this is all zeros in the host portion. Now we've defined the host portion by the mask, right? So what if I take and put all ones in the host portion to get my high address in the range? Whatever the address space is, right? So it's, now we're going to do and the question is, what does this number come out to be? Well, the high address in the range then is, we know that's 255. It's just 8 ones. What is 5 ones? Well, it's just 31. So it's 16 plus 8 plus 4 plus 2 plus 1, which gives us 31. So this range then becomes 172, 16, 31, 255. How many hosts is that? Well, it is 8,192. Well, how do we figure that out? Well, it might be that we did 256 and then 512, 1024, 2048, 4092 or 4096, and then this value here, we know it's 8192, but is it really? We say that it's 00 to 31.255. Now, what are the usable hosts in this particular subnet? We would say that they are 192, geez, I keep doing that. We would say it's 172.16.0.1 because this is the subnet ID. And we go to 172.16.255 to 254. Again, one less than the possible address space. So the usable in this case is not 8192, it is 8190. Right? And where might a router sit? Well, it might sit right here on the top of this address space. Okay, what's our second subnet? Well, we're going to take a look at this address space and we're going to say, what is one more than that? Well, one more than that winds up being 172.16.32.0. Well, what does that look like? Turns out that 32.0 looks like this. which starts to mean that if we look at our binary patterns, we see 0, 0, 0 in the first octet, or in the first subnet, and then we see 0, 0, 1. I'm sensing a pattern. So now if we take this guy, and we do like this, and we convert that to a 1 right there, then we find out that our range is 172, 16, 63.255. And we can see that right here. So it's 32 plus 31, and then 235. Usable, still 8190, but the range now is 172, 16, 32.1 to 172, 16, what would it be? 63.255, or 254 is our usable. Okay, let's go again. Our third subnet. Well, 172, 16. What's one more than the last of the previous subnet? Well, it would be .64.0. Okay, that looks pretty good. But now I'm confused. I don't know. How am I going to add 8,192 to this, or 8,191 to this? And the answer is you don't have to. Just do the binary. What does 64 look like in binary? 64 in binary looks like this. Well, this is the host portion. What happens if we put all ones in the host portion? Oops. And let's be consistent here. There we go. So we get 64 plus 31, which gives us 95. Oops. Do the whole thing. 172, 16, 95.255. Usable, still 8190. Range 172.16.64.1 to 172.16.95.254. And so those are our first three subnets. And you follow right along, and maybe I'll do the last subnet. I don't know. I'm really confused here. Can we jump ahead? Can I do this without doing them all in between? Well, we're just going to follow the rules. And spelling. Okay. Well, what do we know about the last subnet? We know that the last subnet is going to have a couple of things. We know that the last subnet, if we're looking at our binary patterns, and we'll just fill them in here. Like that. We know that our last subnet, the 8th subnet, is going to have all ones in the subnet field. So if I come down here and I put all ones in the subnet field, like this, I'm going to get my range. We also know that the last subnet is going to have the same address as the class full high address. And there it is right there. So we know that our last subnet, or the last value in the last subnet, is going to be 172.16.255.255. And all that we did is the reverse. We put all zeros here in the host portion. Well, what does this work out to be? Turns out that that looks familiar, but we're just going by the binary pattern here. It turns out it's 224.0, like that. And our usable hosts, 8190. Right, 2 less than the size of the subnet. And that means that our usable range of hosts is 224.1 to 172.16, 255, 254. And there we go. That is our collection of subnets. Now, you might say, well, wait a minute, that's still pretty big. And that's true, it is, but it's just an example. In reality, you might create 256 subnets in this particular case. Or like RIT, 512, 10,024. You might create a lot of subnets. The only rule is that it's got to be a power of 2. So if I would have said, I want 7 subnets, you would have said to me, you can't have 7 subnets. It has to be a power of 2. So I say, fine, give me 8. And that's what we would do. Okay, I hope this example helps you in your subnetting efforts. All right, so we've just been netting that address space. Remember that when we're subnetting, whether it looks like we've got an enormous address space still when we're done, what we really did in these examples is reduce the size of the address space that we're concerned about. In the first example, we did a class C, and we divided the address space up into 4 equally sized subnets having 64 possible addresses in each. In the second, we did a class B. We divided it up into 8 subnets. Each one was smaller than the 65,536 possible addresses in the class full address space, and instead we wound up with 8,192 possible addresses in each of the 8 subnets. And what we did was we changed the mask. We took the host portion and we changed a couple of those bits in the host portion depending on the number of subnets that we wanted. Well, that was fun with subnetting. Like and subscribe if I helped, and may those packets always reach their destination no matter what subnet you're starting from.